Okay, so welcome to the 26th video in the Discrete Structure series. In the last video, we had a look at the rules of inferences, and we'll continue this video with a specific focus on problem solving today. And we'll be looking at problems that require us to use rules of inference to prove validity of arguments. However, before being able to solve this problem successfully, we want to prepare by knowing a few things. So we'll be looking at fallacies, just so we know what to avoid when we get to these problems. And then we'll be looking into the extension of rules of inference for quantified statements. Therefore, these three are going to be requisites that we need to know, and this is going to be our focus. I'll start this video with fallacies because this is something that we looked at in our last video. But if you don't have an idea about the 8 rules of inferences, you definitely want to go back and check them out first. That said, let's get on to fallacies. So a fallacy is basically an incorrect reasoning process. And therefore, fallacies are often the cause for mistakes in proof. Fallacy is a very broad concept. There are multiple ways for us to make mistakes. So to narrow it down a little bit, here we'll be looking at 2 specific fallacies that are relevant in the proof methods involving propositions. Let me demonstrate by writing a premise and a couple of inferences. Okay, so I've chosen a common premise here. If you study, you pass. And there are these 2 premises that will apply separately in these 2 cases. And I've written a conclusion in both sides. And so let us begin by looking at this first inference. So I have my first premise here. It says that if you study, you pass. And the other premise says that you didn't study. Can I conclude that you didn't pass? And if you have been following us for the past 2 videos, you know that this conclusion is wrong. Because we know that there is a possibility to cheat and pass. Therefore, the fact that I didn't study is not enough to conclude that I didn't pass. And this is called the fallacy of denying the hypothesis. And a simple way to verify this technically is as follows. The first premise is just a basic implication. Studying implies pass. And you can see what I'm doing in this inference. There is another premise that gives me not S, and I'm using that to conclude not P. Therefore, I'm making the mistake of using S implies P to conclude not S implies not P. And the reason it is wrong is because S is not the only thing that could cause P. In our case, another thing like cheating is also causing P. Therefore, the fact that S didn't happen cannot be used to conclude that P didn't happen, because you could see that C could still cause P to happen. So similarly, we'll be able to see another fallacy here. This premise is suggesting you passed, so I'm given P and I'm using that to infer S. So from my original premise, S implies P, I'm concluding P implies S. And this same example is enough to disprove this. Study implies pass does not guarantee that pass implies study, because you could have passed by cheating. And this fallacy is called the fallacy of affirming the conclusion, because you can see that we are affirming the conclusion of passing here, and that is causing the problem. In this case, we are denying the hypothesis. We are saying that you didn't study. So by denying the hypothesis, we got into this fallacy. And one last thing for you to consider, whenever I have P implies Q, you should know that not Q implies not P is true. And the contrapositive is the only thing that is equivalent to the original statement. Therefore, whenever I have P implies Q, I can only do 2 things. If I have P, I can conclude Q. And if I have not Q, I can conclude not P. And these 2 fallacies arise from the fact that one, I'm concluding P from Q. I'm saying Q implies P, that is wrong. And another fallacy comes from the fact that I'm concluding not P implies not Q. Okay, this is also wrong. So if we can just remember this one fact, that the main implication is equivalent to its contrapositive, you can get to the fallacies by simply inverting them. So from P implies Q, one fallacy will come from Q implies P, getting the inversion. And you know that P implies Q is also not Q implies not P. And if you invert that, another fallacy will arise. And that is not P implies not Q. And so not P implies not Q is this fallacy, denying the hypothesis. And Q implies P is this fallacy, affirming the conclusion. So I hope all of that makes sense. We'll next look at one little topic before we dive into problems. Rules of inference for quantified statements. And let me demonstrate this using a chart. Here we'll look at 2 things, instantiation and generalization. And there are 2 types of doing these. So let me also divide this into columns. So I can do it universally, or I can do an existential one. Alright, so the best way to remember these is by their names. So this one is called universal instantiation, and the name is enough. From the universe, I'm just taking an instant. So if something is true for the universe, for all x, if something px is true, I can conclude that it is true for one instance. I can conclude that pc is true where c is one of the values of x. Every planet is round means that the Earth, being one of the planets, is also round. So this is all that is saying. And on the generalization side, it is just the opposite. If I know that PC is true for any C in domain, I can conclude that for all x px, where x is any member of the domain. And this looks quite pointless, to be honest. PC is true for any C in the domain, and therefore we say that it's true for all. It is correct, but what's the point of even having this rule? You see, often during proofs, things are symmetrical and any random choice will represent the whole population. Let's say I want to prove a fact about the diameter of a circle. I want to show that the diameter of a circle is 2 times its radius. I start my proof by drawing a random circle and drawing a random diameter. And I'll just show for this particular circle and this diameter that the radius is half the diameter. And because of the nature of the circles, because of its symmetry, I'm able to conclude that all circles can be inferred similarly. So the process of generalization helps you to prove something for one arbitrary representative of the population. And as long as that member is arbitrary and could be replaced by any other member within the domain, you are able to successfully infer for all x px. So please make sure to avoid all confusions. We do not mean that PC is true for any one C in the domain, but we mean that it is true for any general C which could be swapped for other C's from the same domain. So this expression for all x px truly requires x to be true for all members in the domain. And if you can find a generalized member that can substitute any member in the domain, proving it for that member is enough. That is all we are saying here. Okay, next we'll look at existential instantiation. So assuming that there exists x px, I can say PC is true for some C. Oftentimes we know that something is true and something exists, but we don't know exactly what it is. For example, for centuries we have known that the circumference of a circle divided by its diameter is the value of pi. And we knew that this value was greater than 3 and less than 4. So it should be somewhere between there, but we didn't know exactly what it is. Therefore, we knew that there existed at least one number between 3 and 4 that would be the value of circumference to diameter of any circle. And this conclusion is just suggesting that one such value must exist based on the given premise. And next, let's look at existential generalization. If I have PC is true for at least one C in the domain, I can conclude there exists a x px. So really simple rules at face value, but these are really important rules. We'll apply these rules and the rules of inferences learned in the last video to solve some problems next. So let's dive into solving some problems now. And all of our questions will have the same requirement. Use the rules of inference to validate the following argument. Okay, so let me write the first question here. Okay, so we'll start with an easy problem. Everyone in discrete math has taken a computer science course and John is in the same class. So John has also taken a computer science course. And the first thing that you need to do is to translate these premises and conclusion into propositional logic statements. And we'll be applying the process of inferences and also the instantiation and generalization that we learned earlier. But it is very important for you to know which rule to use, because what will end up happening is that you'll know all the rules, but you'll not know which rules to apply. Okay, so let us begin by writing propositional functions, and you know that we could do that in multiple ways. And the general guidelines are you want to avoid redundancy, be too simple or too complicated. For our case, let's begin by assuming D of S as S has taken discrete math class. And let us have another function C of S which suggests that S has taken a computer science class. Okay, and once I do that, my premises become these. And if you are unsure how to convert these sentences into predicates, we have discussed that on the translation of English sentences into predicate logic. So we'll borrow the concepts from there and write our premises. So the first premise that I want to write is for all students. If that student has taken a discrete math course, they have also taken a computer science course. So I can say D of S implies C of S. So we have our second premise that says that John is in discrete math class. So we'll just represent that by writing D John. Okay, and these are my two premises. And once I have my premises, we go for the inference step. So this is the step where I need to use these two premises in order to get to my conclusion. And if you want to be complete, maybe it's also worth mentioning the conclusion. So the conclusion that I am aiming for is that John has taken a computer science course, or C John. So how can I use 1 and 2 and the rules that we learned earlier in order to reach C of John? And before we start to infer, let's see what we can do. For all students, studying discrete means studying computer science. So this rule would also apply for John. For John, studying discrete implies studying computer science. And we know that John studied discrete and therefore we can say John studied computer science. So that's the logical flow. But how do we actually formalize it? So I'm going to write my inference steps. I'm going to first use universal instantiation to mention that this fact is also true for John. So since for all students this is true, I can conclude that D of John does imply C of John. And every time you infer, you want to mention the rule of inference. And here you should mention which concept or which rule of inference you used. And in this case, I've used a universal instantiation on statement 1. Okay, you want to write this in full, universal instantiation on this statement. My second inference now is just C of John. And how can I tell this? Since this implies this and the premise is true, this follows from modus ponens. In hindsight, I should have called this 3 and called this 4 because I want to refer to them uniquely. Okay, and we are applying the modus ponens between 2 and 3. And to remind you, modus ponens suggests that P implies Q and P allows me to infer Q. So this is indeed an easy problem, but I want you to be aware of the pattern that we use to solve this. So let's move on to the next problem. So let me write down the question quickly. This is actually my conclusion. So I think we can also easily make sense of this. A student in this class has not read the book and everyone in this class has passed the exam. So that particular student who hasn't read the book has indeed passed the exam. So it's quite logical to say that someone who passed the exam has not read the book because they are the member of the same class and everybody has passed. Okay, diving into the solution, the first thing I want to do is identify the predicates. So someone being a member of the class is one predicate. So let's say C of X is in class. Having read the book is another predicate. So let's say B of X represent X has read the book. And there's yet another predicate that relates to passing the first exam. So let's call that P of X. Okay, now I can begin my steps of inference now. So the first statement says that a student in this class has not read the book. So at least a student exists who belongs to the class and has not read the book. So I can say there exists a X who belongs to the class and has not read the book, and this comes from a premise. And in our earlier topic of conversion of English sentences into predicate logic, we have discussed in detail the situations where we want to use an and the situations where we want to use an implies. So if you are confused why this statement is the same as this, you should go back and review those concepts. But for now, moving on to the second premise, everyone in this class passed the first exam. So how can I express that? For all students in X, if they are in the class, that will imply that they have passed. So C of X will imply P of X. And this is also a premise. Okay, so let me get some space, and I also want to note the conclusion. Someone who passed the first exam has not read the book. So I'll just scroll up and mention the conclusion here. So someone who passed the first exam has not read the book means there exists at least someone who has passed the exam and not read the first book. So this is what I want to be able to infer from these premises. So I can see that the conclusion that I want to reach is very similar to my first argument here. So there exists X, that part is same. All that is difference between this premise and my conclusion here is that I have a Cx but a Px here. But I have another premise that suggests that Px is bound to happen whenever Cx happens. So here since Cx is true, Px would automatically be true. So Px and not Bx would also be true, and that is the statement that I want to reach. And I know that the only way to replace this Cx with a Px is by using modus ponens, because this looks like P implies Q, Cx implies Px, and I have Cx, that is P. And from this I can conclude Q, and that would be my Px. And I can simply use this fact to get to my conclusion. And another immediate observation that I can make is for this modus ponens to apply, I need only P here. That means I have a Cx implies Px here, I only need Cx here. But since A and B is true, I can conclude that A or B both are individually true. And therefore that gives me an idea that at some point I need to split this into a Cx and not Bx separately. And from that Cx and this implication I can use the modus ponens to get my Px. And I can substitute that Px in this equation to get to my result. So if you are looking at a problem like this for the first time, you need to be able to create that mental map to reach your solution. Okay, so let me get started with my first inference. I want to consider any instance of this existential quantification. And this applies generally. Anytime you see a quantification, you take an instance, you do whatever you want, and then you generalize back. Therefore, let me write CA and not BA, where A is that particular example of X that makes this true. And this process will be called existential instantiation from 1. So I'm taking an existential quantification and I'm taking an instance of it. So existential instantiation. And from this 3, I could conclude CA. Because since the conjunction between CA and not BA is true, I can say this should individually be true. And why am I taking CA and not BA here? Because that is what I need to use later for my modus ponens and to get to the result. So that map to get to your solution is really important. And this step is called simplification. We looked at this in our last video as simplification of a conjunction. Okay, now I have CA, and in order to apply modus ponens like I need to be able to write CA implies PA. And I can do that by taking an instance of this. Since this premise is true for all x in the domain, it will also be true for the A example that I chose. Therefore, I can write CA implies PA. And this comes from the universal instantiation of 2. And now I have CA implies PA and CA. I can use that to infer PA, and this is modus ponens on 4 and 5. And it seems like I also need not BA because that is a part of my final expression. So let me also infer that. I can infer not BA. It is the same thing, simplification. And we can see here that we need PX and not PX. I have PA here, not BA here, and both of these are individually true. Therefore, I can take their conjunction. So this is the conjunction rule. And what does this step suggest me? The random A that I started with in my existential instantiation can successfully infer this conclusion. Therefore, I'm allowed to generalize this like so. And at this point, you could finish the problem because that is your desired conclusion. Okay, so sometimes you might get problems that do not involve any sentences. So you are given propositions directly. So let me write one question and give you a hint of how to solve it, and then we'll close the video for today. Okay, so I have this question here, and this kind of questions is sometimes tricky because we don't have any sentences to look at, so we don't have a direct meaning of these. I'll not do the full solution to this here, but tell you exactly what you need to do and write the intermediate steps. So these are your premises. This is your first premise, the second premise, and this is the conclusion that you need to reach. And first, let me explain you my thought process. So I have a not Rx implies a Px here, and I have Rx on the right hand side of this implication over here. And I know from the law of contrapositive that P implies Q is the same as not Q implies not P. Therefore, I immediately have this idea of taking the contrapositive of this implication so that I have my left hand side of not Rx, and hopefully whatever I get on the right hand side of the implication should be enough to verify that is equivalent to Px. So when I take the contrapositive of this implication, I'll be able to derive for all x, not Rx implies, I can take the negative of the whole thing. Okay, nothing fancy here. For all x, not this implies not the whole expression like here. And obviously, in order to make this formal, you would first want to write a universal instantiation, exactly the same thing that we did in our earlier problem. And later on, you should generalize that C for all x in your conclusion. So that would be the complete way of doing this, but the demonstration works either way. So let me show you what happens here. So the next thing that I do is apply De Morgan's law. So this expression, when I put the negation inside of it, changes into Px, and you know that this and changes into or, and then I get a not Qx. So this is the right hand of my implication. The left hand remains the same. Alright, so what do I do next? So let me gather some hints. I have my final expression on the left hand side, but on the right hand side, I need Px, which I already have, but there is something else, not Qx, which I want to eliminate. And I have another fact at my disposal. I have never made use of this equation 1 until now. But I know that in order to reach my solution, this premise must be somehow used, because that is a very important shortcut to learn. You should be able to use all of the premises to get to your conclusion, unless the question designer is messing with you. But almost all the time, you can use that as a hint. I have not used premise, so this should come in somewhere. So how do you think we can combine this and this? You should recall the law of resolution that we looked at yesterday. If I have P or Q, and then I have not P or R. We said that by using the law of resolution, I am able to conclude Q or R. And our argument was that P could be true or false. And when P was true, this would be false, and therefore R must happen. And when P is false, this statement requires Q to happen. Therefore, one of Q or R will happen. So we'll apply the law of resolution here, but let's observe the pattern first. I have a P and not P here. They will get cancelled. And whatever are the two that remain, go into my OR expression. So if I'm looking at this and this, how do I resolve it? I can see that Qx is present here and not Qx is present here. So that will cancel out. And in my case, Px will remain here and the same Px will also remain here. So it will just be Px or Px, because see carefully, the values of Q and R is the same for my example. And you know that Px or Px is simply Px, and that will complete your proof. For all x, not Rx ultimately implies Px. Okay, so that concludes the discussion for our video, and for this chapter, we'll be starting next video with a look into proof techniques, and that involves direct proofs, indirect proofs, and other proof techniques that will come too. So I'll see you guys tomorrow with the discussion. Have a good day and bye.